In this session, we're going to have a talk from Muthu and Venkitasubramaniam. He's going to be talking about his experience with some cryptographic engineering. And unfortunately, since I said his full name, we don't have any more time, so we'll take your questions offline. Okay, so take it away, Muthu.
Thanks, Mike Rozulek.
Amazing.
Yeah, maybe I should say it slowly so that it compensates for the time. Mike Rozulek. Never mind. Thanks, everyone. Hope you had good lunch. I'm going to give enough material, I don't know, to sleep or to not sleep. But you can pick and choose. It's great to be here after 10 years, actually. I think I did come to Berkeley maybe once in between, but presenting, this has been 10 years since I last came here. I am currently part of a startup, Ligero. I'm going to talk about some of the works that we've been doing at Ligero. And this is actually, I'm going to be a little bit technical at the beginning, just because I was looking at all the talks, amazing talks this week, and they were technical. And then I realized that for the past year and a half, I've been going too much to blockchain conferences. But bear with me. Towards the middle of the talk, I'll try to do some demos. I could fall flat on my face, but please bear with me. I think a little bit about this talk is also things that were motivated in theory that led to some of the works that we are implementing at the company. I'm also a professor at Georgetown University, but I'm currently on leave in case a lot of you came and asked me, so just clarifying that. All right, so I want to talk about black box and non-black box constructions. And I'm not going to go technical into it. There are levels of black boxness, semi-black boxness, and so forth. For the purpose of this talk, I'm talking about black box constructions, which means that your construction should rely on the input-output behavior of an underlying primitive. And non-black box means that it can depend on the code or the code specifics. And we all know non-black box techniques have been useful, demonstrate feasibility, identify minimal assumptions, minimal general assumptions. And black box, on the other hand, you have the benefit. When you design it, it's usually modular and also bears the promise of efficiency. A fundamental goal is to close this gap between what is possible through non-black box techniques and black box. And I think a lot of when I started my PhD and my work after was motivated by this question. And in almost all these papers, I wrote the second one, that, hey, I've closed this gap, and black box can lead to efficient constructions. And I will admit I didn't know what it meant at the time I wrote it. So I also think I was drawn more to black box constructions because I was lazy to learn beyond general assumptions, like one-way functions or oblivious transfer. If you ask me to write the Peterson commitment, I might take a little time. But it's also because I think my skills were pretty restricted in terms of I could do black box constructions and general assumptions. So I was also drawn to those kind of questions. This is a work by Lindell and Pincus, which I think, in my mind, actually, when I read it, it was a theory result. It's a theory result. It says that you can construct constant round 2PC for Boolean computations, arbitrary computations. But the construction is black box in oblivious transfer and collision resistant hash functions. You can remove collision resistant hash functions. I think you can do it with one-way functions. But to me, this was a theory result. But we all know this actually paved the way to efficient implementations. This opened the floodgate to gobble circuits, gobble circuit optimizations. We saw all the amazing talks in the first day of the Simons workshop, and that this is still a hot topic on optimizing gobble circuits. And to me, this is one of these works that, it's black box. It was trying, maybe that was not their motivation, I don't know, but it's a black box result that indeed did pave the way to efficient constructions. So let me start with a little bit about, I know a lot of works in this workshop were about semi-honest, a few also about malicious. a lot of the research that was driven, at least I was motivated, was about understanding the overhead of active over passive security. And I'm going to restrict myself to dishonest majority. We heard also a lot of good talks in the honest majority setting in this workshop. This is a little bit of an old result. I kind of want to point out some of the black boxness of this research work. We know in the constant round regime for Boolean circuits, the Yao-Garble circuit technique offers one of the best protocols. It has one round. The communication is security parameter times the circuit size. The number of calls you have to make to the PRG is circuit size, and the number of oblivious transfer is n. Now, the question we asked in this work is, can you get an actively secured protocol with constant overhead over this? We're talking about overhead of active over passive, so can we make it constant in this regime while keeping the black boxness? If you don't force yourself to do black box, now you're going to get into other construction, other primitives, etc., and you won't get sort of a clean result out of it, or at least to state it. So I want to say that this work, a lot of work leading to the work of Wang, Ranallucci, and Katz, was they actually got constant in all the parameters except for the last one. So the number of oblivious transfers, they needed bit oblivious transfers of the size of, circuit size times security parameter. So the question is, can you improve it? Really, this was the question that was left open. Although I should say our work was concurrent to them, this is sort of one dimension that was left open. And we answered this question positively in this work. And I'm not going to give the technical details of this presentation, but I'm going to say that there was one key thing that we had abstracted out in this work towards getting a black box construction, which is this primitive called certified oblivious transfer. It's a very natural primitive if you think about it. You should think of normal oblivious transfer. Actually, parallel oblivious transfer, it's better to think that way. The receiver has a few bits, and the sender has n pairs of strings. The receiver wants to receive it. What we're going to add here is some kind of certification that these inputs that the sender chose conforms to some predicate. Okay? So only if this relation holds, an arbitrary relation holds on those inputs, and of course there can be additional witness, there can be a public statement, then the receiver should learn the output. Now, the question is, can we implement this in a black box way and efficiently, right? Because we do want to keep the constant overhead. And we had a protocol, and this is, again, you think hard, like, you'll come up with a few ideas, and then you work it out. You execute oblivious transfer, give some additional randomness, which is not on the slide, so don't take this protocol for granted. Look at the paper for the actual protocol. And then you get a MAC, and this sort of, you can connect what was given in the oblivious transfer to a zero-knowledge proof in a way that the zero-knowledge proof doesn't have to invoke the oblivious transfer in a non-black box way. I don't need to say that my actions in the OT were correct, okay? Which is something that you would need in the active security case should you have to prove something about the private inputs of the sender. Abstracting this out, we gave a reduction from certified oblivious transfer to normal parallel oblivious transfer, and a commit and prove zero-knowledge system where the NP relation did not have to include the cryptographic code of the oblivious transfer. Now, people in the space already are going to see, hey, there are going to be selective abort issues. Yes, agreed. This has to be handled in a higher-level protocol. But the point I want to say is that this required us to construct a zero-knowledge proof system with some particular qualities. In particular, we wanted the zero-knowledge proof to be sublinear because we wanted a constant overhead. We didn't want the zero-knowledge proof to affect the final result, which was the constant overhead from Yao's garbling. And at the same time, being black box and collision resistant hash function or whatever symmetric key primitive, we didn't want to do that. And when we were doing this, Yuval came and said, hey, look, in this ICOS paper, if we instantiate the MPC with the right kind of protocol, we can get this. And in fact, in that paper, the construction we had was the first form of the Ligero zero-knowledge system. So for me, at least, this paper is very dear to me because this kind of opened not just the Ligero system or the company, but being able to do something very efficiently with this MPC-in-the-head approach. OK, so I'm going to go, the second half of my presentation is all about zero knowledge. So I'll just say one slide about this, and then I'll go back to secure computation. This is this Ligero zero-knowledge system. Subsequent to this work, my student came and said, I'm going to implement it, and joined with him this. We had the first implementation of Ligero. It's simple. It's concretely efficient. It's based on an optimized MPC put through the MPC-in-the-head compiler. It's black box and collision rest and hash function, or in other words, in symmetric key crypto, which is great because other constructions at that time required public key primitives. And avoided complex PCP machinery. All you needed here were, in the crypto, or in our language, pack secret sharing, or read Solomon codes if you like codes. OK, and we saw Abhi gave a great talk, and this was, in some sense for us, a nice validation of our work. And maybe I do want to specify here, our company had nothing to do with this. It was all Abhi and his colleague Matteo. They used the Ligero system in their framework, and we heard all the reasons why they chose this as part of the stack. OK, coming back to secure computation, can we obtain this constant overhead on all these parameters? I want to say one parameter that I ignored there was computational complexity. And there are works by Yuval, Benny, et cetera, that are also trying to optimize that, and I didn't talk about it. But on these categories, we got constant overhead. Then the next question is, OK, can we get one time plus the cost of Yao? And the answer is we don't have a black box solution. But now that we got a good, efficient zero-knowledge system, we were asking, can we actually get this by using an efficient zero-knowledge proof to do it in a non-black box way? And in fact, we did this, again, with a couple of my students, and Yuval and Kermit. We did this. We took garbled circuit, and we proved it in zero-knowledge. But we did a little better than just proving the standard thing you would think in a GMW paradigm. We also got a non-interactive secure computation out of it. And the technique I want to abstract out from this was that to be selectively black box. We were black box in the oblivious transfer, but not the pseudo-random generator. Oh, sorry. We were black box in the oblivious transfer, but not the pseudo-random generator. In other words, in the ZKP statement, we just proved that the garbling was done correctly. And roughly, it was using a similar kind of approach. You have your certified oblivious transfer, and we had a compiler from certified oblivious transfer to oblivious transfer in a black box way. We just needed to make sure that the relation was just about AES computations in the garbling. We did this. We actually implemented it. We had to instantiate Ligero in Galois fields, something that Abhi mentioned as well, because AES is well represented in GF 2 to the 8 or 2 to the 128. And this is, again, numbers that are outdated. But just to summarize, I want to say that the communication of the proof is sublinear, because we used a sublinear zero knowledge. So at some point, this is going to be really small. It is going to be a low-order term. Our overall communication would be 1 times Yao plus this proof, roughly speaking. And the performance was, competitive against the state of the art at that time. And I'm sure now it has, in 10 years or, 8 years, things have improved a lot. And so has zero knowledge as well. So, it could still have a fighting chance. OK, so this was about Boolean circuits, constant round. What about arithmetic circuits as well as multiparty computation? But how do you frame this question? Just like we did it for the two-party, we said you have access to pseudo-random generators and oblivious transfer. What do you want to do in the MPC or arithmetic circuits? Well, there's the first thing that would come to your mind is some form of extension of oblivious transfer. Could be OLE, but it can also be, again, secure multiplication. And I'll show that it's not a big difference between OLE. So we wanted to think about designing efficient, actively secure protocols in the multiparty setting and arithmetic circuits. But we wanted black box and efficiency in mind. So you restrict ourselves to thinking, look, you don't have access to anything else. You can have symmetric key plus secure multiplication. What can you do? And this also forces you to not use things like FHE, IO. And again, no comments. FHE is getting efficient every year. So that could still be efficient in this regime. And we also force ourselves to not rely on specific assumptions. And this helps. I mean, at that time when we published this work, threshold additively homomorphic encryption was the best way to generate this secure multiplication. Today we have PCGs, et cetera, these things that can do it far better and far faster. So being black box and not relying on the specific assumption helps. OK, this is secure multiplication. Each of us generate random shares, and all we want to do is randomly sample two numbers, multiply, and get the shares of the output. That's secure multiplication. It's one step from here to get a triple. You just need one party to adjust their share so that the shares, they have shares of a triple. OK? So if we had to abstract the state of the art at the time we were working on this problem, in the Boolean case, roughly we knew the answer to this. Like we could get constant overhead, even thinking of secure multiplication, both for Boolean, arithmetic, in the two-party setting. But in the multi-party setting, this was open. The best we had was an order S, or security parameter overhead, to amplify passive to active. And again, I'm ignoring here, I think if you have amortized setting, et cetera, some things can be done. But I'm just asking the plain question over here. And in joint work, again, with Kermit Yuval, Antonio, as well as later with Moore, we showed a framework where you can get constant overhead in all these regimes. Okay? If I give you secure multiplication as a gadget, we give a constant overhead in all these regimes, and even not just dishonest majority, the same thing works even in the honest majority setting. And moreover, in practice, we can get this overhead to be 2, meaning I need access to like twice the number of secure multiplication compared to the passive setting to get a protocol.
Amortize for if I want 1 million multiplications, if I just want one multiplication actively?
No, you need at least some number. I think it's not 1 million, but some order of security parameter to get the 2. We have a table on when I think it'll be 4 at the beginning, but towards like maybe 100,000, it gets close to 2, I think. For small fields, I still want to say that the techniques here rely on what are called algebraic geometric codes, which are not computationally efficient. So there are questions open here like, hey, can we improve this better? Like, can we get this constant overhead and so forth in the two-party and multi-party setting? OK. One nice thing also that came out of this work was, hey, we got this overhead of 2. Can we do better than 2? Right? And that was, we used, actually, I should also credit here that, the first work, we used MPC-in-the-head for zero knowledge. All of these works were inspired by IPS, which took MPC-in-the-head for amplifying to active security for the multi-party, for the secure computation setting. So we use secret sharing. We use packed secret sharing in all of these works to get these results. And now there was this beautiful work by Fabrice, Akshay, Yuval, and Tal that showed that Reed-Solomon codes actually had some leakage resilient properties. I remember this was probably the last work that I read cover to cover, and I literally verified every math from the beginning to the end. I just really love this work. What this work really said is that in Reed-Solomon codes, in addition to getting the T out of n, whatever threshold you keep, I can give you T full shares, but I can also give some leakage on the remaining shares, and I still get statistical privacy. Okay? Now, leveraging this, we can actually show that instead of thinking of amplifying passive to active, you can amplify something that is leaky to active. So imagine these triples or these multiplications that you do, you leak a little bit on these things, it will still be fine. And if you think about using lattice-based constructions for threshold additively homomorphic encryption, it's really about being more flexible on the noise, which reduces the key size, et cetera. It has those benefits. The overhead can be close to 1 for certain parameter regimes. And this work also inspired some other question that we were working on ZK PCPs. So what's a ZK PCP? I have just one slide about this. It's really standard PCP with a ZK property. And what you care about in these constructions is sort of a query gap measure, which is the number of queries you have to, the honest verifier should make for soundness versus how many queries the malicious verifier can make for privacy. And the second is adaptive versus non-adaptive queries. Does the verifier have to query first and then look at the answer to get the next query on these PCPs? And of course, you want the gap to be, this is the desirable outcome. You want exponential gap, and you want non-adaptive verifier. Now, the previous results, they had exponential gap, but they didn't have one of the other two things. They either required inefficient simulation, meaning that it was not polynomial time simulation, zero knowledge, or either that or it required adaptivity. So using this leakage resilient secret sharing, we had an alphabet reduction method to show that we could get non-adaptive verifier with efficient simulation, but not the best gap with quadratic gap. And I want to say recently this was improved by Gurr, O'Connor, and Spooner, and I don't know if Nick is here, but I saw him around. They show all these three properties. I think it's going to appear in stock or Fox. Stock this year appeared in stock. That's right. Great. So I want to say here is still a question. Can we construct active MPC with communication that is 1 times passive GMW plus sublinear? And I want to say that black box, standard assumptions with, you have to treat passive, like even triples generator or any of these things in a black box way. Okay? And of course, what you can, if you want to frame this question, imagine that I have something like PCGs that can generate many parallel triples at the same time and some symmetric key crypto. Can I amplify passive to active with smaller overhead? Okay, so that kind of concludes a little bit about the technical part of MPC. So forth, I'm going to go a little bit into things that we built in our company, and there are going to be, I'll also talk a little bit about the technical challenges in that. Okay, so we started this company, at least Karmeet and I, we started this company because, hey, like we have these efficient protocols we're designing, Ligero, the 2PC protocol, I think we called it Leviosa and so forth, and we were like, can we do something with it? And that was our motivation. We started the company. This was one of the first projects we got. This project was about doing distributed RSA generation, okay? And the requirements I'm going to give you in a minute, it was about generating it with dishonest majority among 1,000 parties, but we tested our system up until 10,000 parties. What's the goal? We want to securely sample an RSA modulus, okay? Or a biprime, if you want to call that. We wanted to use MPC. Okay? There is no inputs to this computation. It's just randomness. We have randomness, and we want to sample a product of 2 large primes. So here were the requirements. They wanted a modulus size of 2048, dishonest majority, participants more than 1,000. This was an important requirement. Lightweight. In other words, we wanted the participants to be able to run from either a phone or a laptop where you're memory constrained. So imagine, like this was literally the requirement we got, 2 gigabytes of RAM memory. It should be communication efficient, should not require gigabytes of transmission. And again, this was the requirement they gave, 60-bit statistical and 128. Maybe if they ask us now, they will up it to like 80-bit security. Okay, what did we do? Standard blueprint, design a passive protocol, amplify it to active. There was this beautiful protocol by Abhi's group where they showed a very nice passive protocol to generate these things. And it was really a beautiful idea of sampling a random number is not hard. Checking if it's prime is hard in a distributed way. So one of the key ideas in this work was about sampling this where you have a higher assurance of it being prime. And the idea was that, hey, just make sure it is not divisible by the first 700 primes or something like this, right? And it's possible to generate this using triples in a way that they are not divisible by these things using Chinese remaindering. That seems to be a theme in like Abhi's stuff, but yeah. And then you have to securely multiply to get your modulus, and then you have to test for biprimality, and these relied on works from a long time back. All right. So what did we do? We were like, OK, we have an efficient zero-knowledge system. Let's try to design this. Let's make the communication small and amplify this to active security. This is the standard GMW paradigm. Here, there are no inputs, so you can do better, right? Just execute the entire protocol, and at the end, there is no loss of privacy by not doing it in between. Just at the end, you give a zero-knowledge proof. And again, I want to caveat here by saying that there's still selective abort attacks, et cetera. We are in dishonest majority. That's something that you need to worry about. But this is a protocol where at the end, everyone just gives a proof. And we implemented this. I want to say that we needed to generate triples. We used threshold additively homomorphic encryption. Daniele helped us with the parameters using lattices, et cetera, to get very good triples generation. Just extending this idea of, I talked about certified oblivious transfer. We imagine this again, just to be strategically black box when we design these things, we extended it to a certified triples functionality. So the idea is that, let me just go into the thing. Here is the certified triples functionality. You imagine a phase one where everyone gets the triples, and then at the second phase, everyone proves they used their triples correctly. And you need some framework to commit what you have done and then prove it. But the idea is, again, we didn't do it in this work, but if you wanted to, there is a way to securely reduce this to certified triples in a black box way. In this work, we actually did everything non-black box in the zero knowledge. All right. So this was our protocol to get the certified triples functionality. You commit to your randomness at the beginning, do threshold additively homomorphic encryption, and prove that you did all these lattice operations correctly. Now, they're a pain. Lattice operations, they work on these huge moduli that could be product of primes, as well as you have to prove noise bounds, et cetera. But in the zero knowledge system, this turned out to not be that impractical. So the zero knowledge had to do, these were just the kind of things that went into the constraints. So triples generation was, again, for threshold additively homomorphic encryption, our modulus was, I think, 13 or 14 of these 62-bit primes. That's how big we needed for the right security level. Then we had to prove that the triples were consumed correctly. And then finally, there was the Jacobi test, which is like a sigma protocol, if you want to imagine, right? And we had to prove in zero knowledge that we executed all of this correctly. Our solution, again, we used the Ligero proof over the ring. And the nice thing is that you can just imagine it as proving individually on these primes, essentially. So that helped us. So you can, in parallel, do these, just do n proofs. Again, you have to do some stitching across these things. But proving on this ring ZQ was not hard. But the Jacobi test was best proved using a sigma protocol. Okay, you're proving knowledge of some exponent, and proving that was best done by the sigma protocol. We combined these two. We did a composition using max. Again, this was an idea that Abhi mentioned in his work. If you have two proofs and you have common variables, you can use some kind of MAC to connect these two. These were the parameters if you're interested, but I don't want to go into that. I want to say we ran this, and actually this was, we were really proud. We were able to run this 1,000 parties. After running 1,000, we were like, OK, let's run 10,000. And the generating triples and the passive part, they work very nice. The zero knowledge does take time. And there was one design choice, you can come and ask me later, which was bad, and that kind of spoiled the UX. And I can tell you what it is later. But even at 4,000 parties, it took about 4,000 seconds to run the passive protocol. And actually, 1,000 parties, we were able to bring the passive part of this protocol. Oh, actually, the passive part at 1,000 was 5 to 6 minutes. We ran it on these. The parties were exactly according to the specification. two cores and 2 gigabytes of RAM. We introduced this thing called a untrusted coordinated model, which I'll tell a little bit later. Okay. This was the first project we took at the company, and we had to design these things. We published this work. It was great. The second one, we were now deeply thinking. One of the things I would encourage everyone here is to deeply think about a useful product to build out of MPC. And when I say not the technical challenges will not be hard. It's about building an end-to-end system around this thing and asking, how are you going to convince people to use this technology? So we built the system, the Meshcal, and you would think this is sort of a very natural thing you would want. Today, if you want to coordinate a meeting with more than 2 people, the best people have is either when to meet or exchanging emails. You should use MPC. Now, again, I will caveat it. That's really not accurate, but it's a prime problem to solve using MPC. And I'm running a little short on time. I was going to show a demo of this, but you can go meshcal.com. You can go, this service is available to use MPC to do it. Currently, we do MPC in the cloud. Okay? We don't do it on the users. Again, one of the challenges when you want to build these products is UX. UX means that you cannot have someone say, I'm going to run MPC on your computer. You got to wait like 1 hour, like with your browser open. That doesn't work. Like it has to be non-interactive. As Abhi said, squashing the rounds. Like this is really important when you design these things. So we did with MPC in the cloud. I want to say the MPC itself, we had a general purpose MPC that took probably 2 or 3 months. We had already had enough infrastructure. But the UI UX, we spent a year. In retrospect, you will agree with me, there was a waste of our time a little bit because the challenge here was not MPC. And I'll just say, Nee was asking me just before the thing. She's working in this as well. And she has a system too. So all of you go check out her system. The challenge is really we don't know how to solve this insecurely. I mean, there is Calendly, we all know. Like, it's beautiful. It's asynchronous. Like I give you a link, you manage your preferences. And here we don't know. People manage calendars differently. There are people, OCD people, who everything is like on their calendar. And there are people, when I was doing this, I went and asked Rafael, he's like, what's a calendar? And like, everything is in his head. So you're going to have these wide spectrum of people who are trying to be on your system. And some people are going to have priorities. And even when I look at calendar and I'm looking at to schedule a meeting, I'm like, hey, no, I have to go pick up my kid. I have to take there. And these are not on the calendar. So we don't know how to solve this insecurely. If we know that, I will guarantee to make it secure is not hard. All right. After this, our focus was more on fintech enterprise kind of applications. The next natural application we all talk about in our classes is auctions, right? So here is a simple problem. We have buyers and sellers. They have, the asset they want to buy, the price, the volume. And you want to match them, okay? And the whole idea is like you don't want to reveal their intentions or what they want to buy or how much they have. This is called front running. You want to prevent it. People like institutions with huge assets that want to trade, they really do care about this privacy because if they go announce it even to a market maker, etc., there are going to be hedge funds, etc., those people who will drive up the price, which is called front running, and it makes the market inefficient. So MPC, again, is a prime example to do this. Now, there were a few approaches. Again, MPC in the cloud. Again, in the interest of time, I'm not going to say this. I just want to say that here was sort of our challenge. Our challenge was we wanted to do parallel auctions on, say, 1,024 assets, or symbols, as they call it, among 30 participants. So think of first price auction, not second price auction. And we were able to do this in 5 minutes. Okay? It was really a scalability challenge. You had 30 parties. You wanted to do 1,000 auctions in parallel. And imagine that each of these numbers were like, 16-bit or 20-bit numbers that you wanted to do the auction on. Some of the things that we did well over here is a model where we have an untrusted coordinator that can do this, meaning that I don't need to trust the coordinator to do the actions correctly. We can protect against a malicious coordinator, except for liveness. If the coordinator goes offline, then your computation can stop. But again, this you can improve by redundancy, have multiple coordinators, etc. Another thing is we wanted, again, the thing that we took away from the RSA project is we wanted to stick with being on the browser. So this protocol that I'm telling, actually we have a demo that runs where the clients run from a browser with restricted memory. And we used the certified triples functionality. Here, everything was black box, actually, and an end-to-end implementation. So these were sort of 3 of the MPC projects. If you ask me what business we made out of it, come and ask me later. Don't want to officially report it in anything that is recorded. So these were the MPC projects that we had taken up. But in the same time, I want to say thanks to Rafi here. He let us participate in the DARPA SEEV program to work on zero knowledge. And we had this Ligero system, which we used it inside the MPC in different ways. But this DARPA SEEV program was about getting efficiency. It was about, it was not about blockchains. It was about doing zero knowledge of trillions of gates of circuit from commodity hardware. Now, most of the teams used interactive VOLE-based zero knowledge because that was sufficient. It was about proving, hey, programs were memory bug-free or compilation and these kind of statements. But we said, let's stick with ZK snarks, or like we want to be non-interactive, publicly verifiable, and we stuck with being that and trying to reach that goal. So that work actually culminated into the next version of Ligero, which I want to talk a little bit about in the remaining 20, 25 minutes I have. Okay. And there will be demo. Okay. All right. So what happened to the ZK dream? And we heard a lot about this from Abhi on how he is trying to really get ZK into the phones of billions of people. And it's an uphill battle, and it is not for reasons related to cryptography at all. So from promise to practice, why has this still been a niche? Like, I mean, okay, MPC, coordination, there are many things you want to think, but ZK is a clean thing. Like, and there are applications. Why is it still, used in corners of, applications? First answer, we don't care about privacy. Institutions care only if regulation asks them to. PMF is not probability mass function, it's product market fit. Has not been identified. We don't know what is this killer application of ZK. DSL is a barrier to adoption. So DSL is this thing called domain-specific language. And in our words, it's like the Bristol format, or the way we represent MPC circuits, or ZK, which is R1CS. And is it that it's hard to program in these things to get these applications? Or does it require heavy hardware? And I was not here in the proofs workshop, but I would imagine that these things today, they use tons and tons of hardware. Okay, they use like 30, 40 GPUs connected, and it's been amazing work in terms of I can get very high throughput in terms of how many gates per second I can do. But it requires heavy hardware. And if you think about ZK, it's often about individuals proving sensitive information. You cannot expect individuals to have 30 GPUs, on their premise. And the final, which I can't, stress enough, is UX. If we don't get a good UX, there is nothing else that matters. Like, the adoption will not be there. Like, if you cannot make it easy for people, if you still say, like, I have to go to command line and do something, like, that's it. Like, you've already lost like 90% or maybe more than that of the population to use your technology. The zero knowledge landscape's been great since the advent of blockchains. There is billions of dollars that are being poured. We got, thankfully, some funding last year for developing our ZK. Now, I'm going to go a little tangential in terms of these things that are challenges in ZK. I want to go to programming. We started programming with with punch cards. Actually, that's my dad on a punch card system over there. He was using an IBM punch card system back in India when Indira Gandhi at that time was testing the hydrogen bomb. He was doing like meteorological calculations on the punch card. He would tell me that, hey, in the morning, I have to give this program and I'll get the answer in the evening. If I made a mistake, good luck. Tomorrow you have to try it again. We lost him at COVID. So just a little homage for him here. The first machine I worked on, that's actually me, with my brother, was a IBM PC XT machine. And the first programming language my dad taught me was COBOL. This is plain English if you look at COBOL. And in fact, financial institutions still use COBOL in many corners. If you track the evolution of, and I hope these years are okay. I checked with Wikipedia, not with ChatGPT. The 40s were punch cards. Then came COBOL, Fortran. Then we got C, Unix. And C has survived the test of time, if you think about it. Then from 70s to 2000 was the birth of object-oriented programming, C++, etc. Actually, the first language I learned object-oriented was something called Smalltalk. It was one of the first object-oriented programming languages. But today, we do vibe coding. So let me step out of this and show you. Oh, actually, before I do that, I should not assume. So let me tell what is vibe coding, right, before I go into it. This is my high school classmate. He's a professor at Princeton. Aravind Narayan has done a lot of influential security works. He also has very nice hacks. And I go for these hacks when he posts it on LinkedIn. And he put this where he said that he could code these 5-minute apps for his kids to teach something. I have young kids, and I also, they're learning math and they're doing these things. I was like, can I do this? Now, vibe coding was coined by this guy, Andrej Karpathy. I can tell you more about him if you want, ask me later. He said that today with these LLM tools, I can build apps without touching my keyboard. That's vibe coding. Really, that's vibe coding. So let me show you, when I saw this, I was like, OK, I've not coded, I do run a company with engineers, but I have myself not coded for for more than 10 years. So I actually made this app. My 5-year-old is learning addition. You can enter the right answer. It's a very simple app. The first app took like half hour, but after that, all the apps, after addition, subtraction takes 5 minutes to do. And also, for people who came here for karaoke, knows that my 5-year-old likes Frozen. So then she also wanted, every time, I don't know if the sound will come, but no, that's OK.
Wow.
That's like Elsa and Anna saying wow and no. I was able to put this in the using vibe coding. So once you do this, the next question is, hey, can I use this for teaching? Right? These 5 minutes apps are going to be great if I, to do this. And I had an app for pack secret sharing. But what I want to show you, another one, is this, a single line code. And I'll share the prompt to do the 8 queens chess problem with a fancy UI. And I think here it is deployed, where, you can, I'm just going to use the show hint. It can, you can also play with it, and this is a 8 queens chess problem. And it was just a single prompt, and I could deploy this this app on GitHub pages. All right, so that's vibe coding. Now, talking about ZK evolution, in the beginning, we know the feasibility of ZK was established through reduction to NP-complete problems like graph coloring and Hamiltonicity. Then we designed proofs for Boolean and arithmetic circuits. And then since blockchains, this has improved rapidly. And today, there are these things called ZK VMs. What are ZK VMs? I can prove a virtual machine instruction set. And the popular ones are like RISC-V and WebAssembly. The advantage is I no longer have to hand code circuits. I can write my code in a high-level language like C++ or Rust and compile it down to these VMs and just prove zero knowledge of these. Now, just comparing this, I'd say that R1CS and Groth16 in some sense are like punch cards. Once you do this trusted setup ceremony, you're stuck with it, right? But now we have improved this both on language, on ZK end, and we can do these ZK VMs today. But what I want to show you today is vibe coding. I mean, if you have done C++ and Rust, why not vibe code, right? I mean, if your LLM can generate these things, why not vibe code? And I should tell you that I was trying this morning, and it didn't work. And the reason was that GPT upgraded, OpenAI upgraded to ChatGPT 5, and it started doing weird programs as opposed to simple programs when I asked. Nevertheless, I'm going to try it to show you. But before I do that, I kind of want to show you what we have built. We have built a platform at Ligero that's going to make it very easy to develop and deploy zero-knowledge proof systems. Okay? Now, we have a marketplace. Again, everything is open now. You're not charged. And even if we were, you come and ask me, you'll all get it for free. These are different applications that have been designed on the platform. I'm just going to pick one of them, Merkle root. So let me show you the source code. The source code is actually written in C++. And really, the Merkle root is about verifying a Merkle decommitment. I'm going to give you a leaf, a root, and the Merkle path. Verify it under zero knowledge. This is very commonly used in blockchain applications to prove transactions, etc. This is one piece of the puzzle. And I'm using the SHA-256 hash function. This is the source code. And for all of them, you should be able to see the source code. I can prove this straight from my browser. Okay? So these are already deployed applications. I want to say that one of the things that differentiates us from others is we are trying for sensitive applications. You don't have to go for a TEE or a remote server or MPC. You can prove things straight from your browser. So I'm going to do one of these, and let's see if it works. This is ChatGPT 5. I had to give some instructions because the way you do assertions in zero knowledge, I have to tell ChatGPT, when you do the code, please use these right APIs. So that was the first part of that. And now I'm going to try to do this. Let's see what happens. Write a C code that takes as input in command line 3 strings. It computes the edit distance of the first and the second string and asserts that it's less than 10. It also asserts that the SHA-256 of the first input is the third input, and the second and third inputs are public. All right? So I haven't touched my keyboard yet. So let's see how much time it'll take. Yeah, this has been the new feature of this ChatGPT 5 that's been annoying. Previously, it used to just give an answer pretty quickly. So
immediately came up with a catchy phrase for the task: input to previous edit distance.
Faster than I would do it.
Sorry?
Still faster than I would do it.
All right, so it did it. OK, this looks pretty complicated, but let's try it anyways. So I'm just copying this code. I'm going to go here. I'm going to create a new project. Let's call it edit. This is one of the things you can do in the platform. You can drag and drop programs. You can compile it. Let's see if it compiles. OK, it did. That's at least first step. And now let's see if I can run it. I have to give 3 inputs, if you recall. I already have the SHA here. I don't think I can do that from memory. Oops, sorry. OK. I'm going to mark this private, and then I also will copy the SHA. OK, it ran, but the result is false, so which means that the code is not completely accurate. But
it sounds.
Maybe. All right. So the point, at least, what we are thinking more at Ligero is we want to make this technology more useful and more usable. And given that we have come all the way to like doing C++ and like Rust and like high-level languages, taking it to the next step. And again, I know I'm talking to an audience of security researchers. Vibe coding security applications is probably one of the worst ideas to do it. But that being said, I don't think it's far off from simple applications. Maybe we can also generate, say, a lean proof. This is what Dan Bonnet said recently. It's like maybe within the next 10 or 15 years, along with your code, maybe you could also generate a lean proof that this circuit computes what you wanted. Right? Like this doesn't seem out of what we could probably achieve. So if that can be done, then if this compilation was formally verified, we could do everything using vibe coding. Maybe one last thing I want to say, this is sort of, we have this thing called the MDL verification. You can look at it. I'm not going to do the demo. It's a very mild version of what Abhi did. And I want to say, because we use EDDSA signatures, not ECDSA, and we prove a weaker version than he did. Very strong parsing. We leak some more information in the parsing than he does. But the identity NP statement that Abhi talked about this morning, you can run it from your platform. I want to say this is open. It runs from a browser on your phone. So we did it so that it can run from a browser, and then we tested it on the phone, and it works on that as well. All right. So coming back. So the challenges in ZK design was about first circuit representation, then it was about prover runtime, and from polynomial we made it quasi-linear, just FFTs, and now we can also have linear in the circuit size. But today I want to say the bottleneck is really space complexity. And one of the questions, at least as part of the DARPA project, the research we did was, do there exist time and space preserving ZK snarks? And this was already thought before. It was defined by Bitansky and Chiesa as complexity preserving succinct arguments. They also designed one with FHE, which I'm guessing might not be that efficient. Then there were really beautiful works by Bloch et al. Where they did complexity preserving ZK snarks using more common public key assumptions, discrete log, and then groups of unknown order. But again, my black box, and I can't think of those kind of assumptions. Can we do this in a black box way from minimal assumptions? And I say collision resistance. We don't know if collision resistance is a minimal assumption for sublinear arguments, but if I give you collision resistance, can you do this in a black box way? And we showed that this is possible, and actually that our proof length is roughly T over S. And we gave evidence. Is Benny in the audience? Because when I say lower bound, I just want to make sure. We give evidence that you can't do better than this. And when I say evidence, and again, I'm sure that, we're going to have amazing research that comes out of it, is that all of ZK, as Abhi said, uses error-correcting codes or polynomials, Reed-Solomon codes for their construction. And the statement I'm going to say is about these codes, that you want to have FFTs or fast polynomial evaluation on a set of points. There is a time-space trade-off. So I'm going to tell you very quickly a lower bound in this specific setting. I have an input n. I want to encode it. I have some RAM of size S. Now, the way you would imagine is that you take a linear pass on the input, and then you start writing your code. You might take multiple passes on the input. Okay. Now, since you want efficient time-wise, you don't want to run more than log n passes of the input. So I'm going to put that restriction because I want time efficient. And my space efficiency is about restricting the space that I have, a work tape memory of size S. Now, a simple counting argument will say that if delta is the distance of your code, I can find delta n over 2 contiguous block that can influence only delta m over 2 blocks. And now, again, you can just use the pigeonhole principle, counting the number of codes that can be there, and say that at least 2 of them will literally have the same encoding, except for that region. So this will restrict the delta that you can get from the construction. And really what this is saying is that if you want quasi-linear encoding of constant distance code, like your space needs to be proportional to your input size. Okay? So this puts a severe restriction in terms of what you can get with time and space efficient ZK snarks. Okay, so the last few minutes, I want to say that the new version of Ligero that is memory efficient, we designed this with proof length like T over S. It's, again, take this with a grain of salt. I'm sure works are going to get many more memory efficient, but as it stands today, it's the only memory efficient hash-based snark. ZK snark. It's ZK by default. That's more for the blockchain people because I need to distinguish between ZK snark and snark. I know that I don't have to do that distinction over here. We are a ZK VM, meaning that you can code in high-level languages. Barring my flop on the vibe coding, it does. You can code in a high-level language, and we chose a big prime over here to instantiate our system. Ligero can be instantiated on any prime field, small, big. We heard all of this that Abhi said. But we chose this big prime because we are also trying to serve the blockchain community. I need to verify these proofs recursively using something like Groth16, and having it in a large prime makes the recursive composition step cheaper. But now you want to do big num arithmetic on a phone, etc. If you rely on the CPU sequentially, it's going to be slow. So we have used web GPU. I mean, everyone is using GPUs, but I'm stressing web GPU because it makes it portable. It can run on any device. I don't need an NVIDIA GPU and CUDA programming language to do that. Last, let me just say something about VMs and also relating to what Abhi said. I'll try to go over this pretty quickly. One of the things when you have to do VMs is that you have an instruction set, and you cannot, whether snark or ZK snark doesn't matter, you cannot reveal which instruction is being executed each step. Because even if you want succinct verification, the verifier cannot depend on what each instruction is. It needs to be uniform. In other words, you want a universal circuit for these things. The max overhead really is about the overhead of universal circuits. Okay? Now, and this is, what I mean over here is that how many constraints do I need to be able to process all the different instructions divided by the smallest instruction? For example, XOR might be your smallest, but some addition on like a 64-bit arithmetic is like, or multiplication is the biggest, right? So this overhead actually is a price you pay in the circuit size. Naive universal is just to do a big OR or a big mux. But there are clever ways you can do universal circuits. There's also this work by Thaler and his colleagues, Jolt, which uses something called lookups to do this in a much more efficient way. But can we pay constraints that are exactly as per the instruction? And this is some research that we did. I just want to kind of not go into the details. I want to point out some work that we did with Ibn, David Heath, Vlad, and Kermit, where we actually showed in the VOLE based, and this extends also to IOPs, etc., where I don't need to pay this overhead. Okay, I don't need to pay the overhead of this mux for instructions. In other words, we are going to now, instead of thinking of each at an instruction level, we are going to think of your code as basic blocks, and there'll be a one-time cost on all basic blocks, and thereafter there won't be. And I don't have time to give the ideas on this, but come and ask me later. I will tell you. Again, if you want to try a speed test, like you can scan this, but if you have an iPhone, it's a little bit painful. You have to go set up some feature flags. I hear that iOS 26 is going to default enable web GPUs, then you don't have to do this. So maybe I'll just conclude with this to say that we want to make ZK more useful, usable. Try our platform. If you have any suggestions, feedback, let us know. Thanks. Yes, Juan. So maybe 1 minute story was that when this was the first implementation I'd ever done. Before all of this, like none of my papers definitely were not implementable. All of them probably used card productions, but we had to name it. And I came to Yuval and Kermit and I said, hey, like it's lightweight. Let's use Leviosa from Harry Potter. They're like no Harry Potter reference. So then I went to Google Translate, and like every language I was like, okay, what does lightweight translate to? Right? In Italian, I think it's leggero, and then in this, ligero is nice, right? So LIG is lightweight, ERO is zero, like lightweight, zero knowledge proof system. And today, Hugo told me that it also means nimble, it means fast, like all great adjectives for our ZK system. I might not be pronouncing it correctly, but you can pronounce it any way you like. I have a long name, so I have a lot of tolerance.
Let's thank Muthu again.
45 minutes where you can vibe code, but then...
I'm sorry about that.